Our first target is drawing the graph. What does that demand? It demands values of x, y, and z, but now the difficulty appears. Where do we draw a point with x, y, z, and w? We can't draw 4 dimensions. What does this difficulty demand? It demands fixing one variable. So let z equal 0, then w equals the square root of x squared plus y squared. Now we've got a 3-dimensional slice we can sketch. Here x and y live on the floor, and w is the vertical height. What if we set y equal to 0 instead? Now the xz plane is our floor, and w is still vertical, so we're just rotating our viewpoint, that's all. Now, partial derivatives. Our new target is f sub x at a, b, c. What does this demand? It demands the rate of change in w and only x changes, y and z stay fixed. So we move from a, b, c to a plus h, p, c. Notice b and c do not move. F of a plus h, p, c, minus f of a, p, c, is the change in w. What does rate demand? Divide by h. Are we done? No, we want the exact rate right at the point. So, we take the limit as h goes to 0. Last part, composite functions. U equals f of x, y, x equals phi of t, y equals psi of t. Our goal is du by dt. What does that demand? It demands u in terms of t. So u equals f of phi of t, psi of t. That makes u a composite function of t. Now du by dt makes sense. Now let's upgrade the case. Now x equals phi of t1, t2, and y equals psi of t1, t2. The target is partial u by partial t1. What does that demand? It demands changing only t1 while keeping t2 fixed. So we take the partial derivative with t2 held constant. Target, demand, resolve the difficulty, result. The chain of questions is the method, not memory.